Welcome to our webinar. My name is Greg Mulholland and I'm the CEO of Citrine Informatics. For those of you that are new to Citrine, we create AI and machine learning systems for R&D in the materials, chemicals, and products industries. And we've been doing it since 2013. And so we're really proud to have a real leadership position in this industry and a lot of experience in implementing these AI and ML tools to help companies innovate faster and get their products to market faster. Today, I'm really happy to be joined by Vijay Narasimhan from EMD Electronics. Vijay is their Director of R&D Collaborations and has had a huge amount of success introducing the Citrine platform to the R&D team working on photoresist chemicals in the semiconductor space. Welcome, Vijay.
Thanks, Greg. Super stoked to be here.
Look, I come from semiconductors, so I'm really excited to have this conversation. And there's a constant discussion and drive for more performance, more energy efficiency. I mean, gosh, I can't imagine what you guys are hearing from folks like NVIDIA and others around extreme UV photolithography and creating the ability to create more efficient chips. I know EMD Electronics sells the chemicals that you need to lay down these patterns and kind of do the fundamentals of semiconductor engineering. And I know you all have done a lot of really interesting, innovative stuff. So you've seen a lot of success using AI and the Citrine platform in particular to optimize your formulations and your chemistries. So I'd love to hear what you managed to do with the platform from a technical perspective, because I can talk about it all day long, but you're the one who's seeing the results on the ground. And so thank you for, first of all, being here. This is an exciting moment for me. But also, I'd love to hear about kind of talking about AI and introducing it in the research function from a more practical cultural perspective. So I guess let's start with the easy stuff, the technical stuff. Can you talk a little bit about what you were trying to achieve and what you actually did from a technical perspective?
Yeah, for sure. So we can start by setting the stage a little bit. And we have seen over the last many decades the incredible progress that's been brought about by Moore's law, this empirical law that has basically, it has multiple dimensions, but one of the important dimensions is talking about the density of transistors on chips. And these transistors are the switches that are the ones and zeros that basically allow you to compute all of the data that go into everything from your smartphone to these huge server farms, right? And these AI, these servers that are crunching on AI models. So to keep that pace going, you have to be able to make transistors smaller and smaller. And in fact, all of the ancillary parts that go around transistors, the wiring, the memory elements, and so on, smaller and smaller to keep this pace. And the way that you do that is you have to improve photolithography. This is the process by which we transfer the patterns that define where all these little structures are onto wafers. So the most recent set of transitions in photolithography has been to extreme ultraviolet. Basically, what's happened is that we're using light that has a wavelength of 13.5 nanometers. It's really small. And that really means that you can put lots and lots of transistors onto these chips. Now, at the same time, there's this trend that chips that maybe used to be only about yay big are starting to get bigger and bigger to the point where they're really limited by what's called the reticle, by essentially how much you can cram into one space that you can do photolithography on at a time. And so you have these sort of competing elements where you're trying to make everything smaller and closer together, and you also have to make that work in one shot over a much larger space. And so that's the problem, is that you have all of these little wires, all these little lines that need to come super closely together, and they're really small. And they're very prone to having defects. So those defects could be, for example, you have two lines that are side by side, and then they touch. You have two lines that are side by side, and part of them is missing. And so the other thing entirely is you have two lines that are side by side, and they totally collapse into each other. So there's all these different types of defects that emerge. So in order to control that, right, the light source is what it is. It's basically fixed. You can change how long you're dosing for. But then we have a lot of control with the chemistry. So the chemistries that we're using have about 5 to 10 different components that go into the formulation that serve all of these different functions. So you have one part of the chemistry that captures the light and then turns it into electronic energy. And then that sets off a chemical reaction. But you can't have the chemical reaction go on too long, or else it will spread outside of the area that you need to define these tiny little lines. So then you have another chemistry in there to quench the reaction. So you have all of these different elements that go into the solution. When you think about that, you're like, okay, there's 5, 10 different things. Like, that doesn't seem too hard. But then multiply it out. So you have these 5, 10 different things. There's probably 10 different ingredients that we know of today that we can use, and we're trying to discover even more. And then you have to change the ratios of each of those elements to bring them into this perfect balance so that you're setting all of the properties of this formulation. And so to achieve these competing goals, right? You want it to be as efficient as possible, to require as little light as possible to get the pattern down, to have as low defect density as possible in all of these different ways. It really is this incredible challenge, and we just don't have the capacity to fully sample the entire space that's available to us. And so that's why we turned to the idea of sequential learning, and that's why we're really happy to have partnered with Citrine. So when a regular R&D scientist sort of comes into this situation, usually what they might do is they'll say, okay, I'm going to turn one of my knobs at a time, maybe a couple at a time, so I can see some interaction effects. But usually what's happening is that people get stuck in what we would call local maxima and minima, right? Like you find a space that kind of works, and then you might optimize around that really quickly. But there is a much wider space that's out there. And then more importantly, once you discover that one part of the chemistry works well, you want to know why is it working well? What other chemistries might work well? And so that's where having a model that's able to handle all of this complexity, to balance the idea of optimizing, but also looking in new spaces is so important. And that's basically what we did.
That's super interesting. I mean, gosh, I remember I was thinking back to my undergrad days. I graduated from undergrad in 2007, and I remember it was sophomore year, and people were saying Moore's Law is around the corner from being dead.
Yeah.
We're not going to be able to do this stuff. It's incredible that you're able to continue to push the limits. I mean, 13 and a half nanometers, that's not a lot of atoms in that space. I mean, it depends on the material, but you're not talking about much, especially polymer molecules, right? So how are you thinking about, I mean, what have been so if we turn back the time before using AI,
yeah.
How many experiments, what are people doing typically? Like, what did the world look like before we started working together?
Yeah. So as with a lot of chemistry, I would say that most people were relying on really good foundational knowledge. So we might have been running some intense simulations. There's also just like what chemists know about what reactions go together, and sort of you develop these heuristic pieces of understanding about the system that you would use to guide experiments. And you might even do systematic designs of experiments where you're evenly sampling your space, right? You usually, for example, when you're doing a screening design, which is very typical when you start an experiment, you usually have like a low value and a high value with what's reasonable for each of your parameters of interest, and then you combine those into either a full factorial or a fractional factorial design.
Sure.
So that's what the world looked like. And again, when you are starting with a bunch of effects that are very likely nonlinear, and you're starting with just throwing a couple of darts at the board, very likely you're not going to be sampling as much of the real behavior as you would like. And you also might, lock onto some things that don't wind up being important, and you also may not be able to generalize your findings. So you understand for these particular molecules what happens. But then you really are relying on all the chemical intuition and that kind of thing behind the scenes to go into what's next, like what other molecules could you use, how could you make this better, what groups could you add on, this kind of thing.
Sure.
A really cool part about the Citrine platform when we got started with it was that you're not starting from scratch. You're not basically saying to this ML AI thing, okay, learn everything about chemistry.
Right.
It's chemically informed. It has a lot of descriptors that are the same sorts of heuristic descriptors that experimentalists are using to make these kinds of decisions. And beyond that, also, you can almost hard code relationships that you know of in the system, like what parameters are correlated with which ones are truly independent. And so the way that you design your model through that whole sort of materials history and hierarchy really reflects the way that experiments are truly done. And I think that's pretty game-changing because you have these two worlds. You have data science, you have chemistry, and they don't often talk to each other without needing multiple layers of translation in between. And that's kind of a nut that you all have been spending a lot of time cracking, and I think it shows.
Well, thank you. I'm glad. I mean, look, we've been at this for a minute, as I guess 11 years being that minute. Yes, I agree. But on the other hand, I guess for me, I'm an experimentalist.
Yeah.
I work with theorists all the time. They're wonderful people. But to me, I care about the results. Like what does someone get out of their experimental efforts? And so, I'm really glad that the approach we have taken was useful. What did you actually get out? Like what did you achieve?
And I think the arc of how we got there is almost as interesting as where we got.
Absolutely. Well, I was going to take you there next, but please.
Yeah. So in the end, to make it short, the top 6 candidates that we made in this complex formulation space were all generated by sequential learning from Citrine. All 6 of them, and that's out of hundreds and hundreds of data points that we tested. And that was a combination of both previous cycles of sequential learning from Citrine as well as other experiments that the experimentalists brought along for the ride, so to speak.
Sure.
So that journey was not linear, and it was not exponential either. Like, it wasn't like, oh, great, like we started slow and then we got there, and it wasn't like, okay, we steadily made progress. There were all sorts of fits and spurts and the need for model refinement and experimental refinement as we went. And that was kind of the beauty of the process, and it really is the significant cultural shift to sort of accept this. So right when you start with any kind of sequential learning algorithm, and you don't have a lot of data density, and we didn't. I mean, our experiments, just to put this into context, they cost tens of thousands of dollars per experimental run to complete. They take multiple weeks. We have to have the chemistries available and then formulate them. And we're also doing this at a partner site, right? So with these sophisticated extreme ultraviolet tools, people in R&D like us don't have our own EUV system just like sitting in our fabs. Like, you need
tens of millions of dollars.
Yeah. You need multiple jumbo jets to get them where they need to go. They're possibly the most complicated equipment that humankind has ever made.
And apart from nuclear weapons, one of the most completely controlled these days, too.
Yes, yeah.
It's wild.
Yeah. And so it means that we have to really, choose wisely. That was another really appealing part of using this platform. But when experimentalists saw the first candidates come out, they're going, oh, gosh, like, I know that's not going to work. Why am I doing this? Why am I spending the $10,000 to do this experiment? And I think that is part of the process that you have to kind of learn, right, is that the model needs time to pick up on all these relationships that you have had in your brain. You can either hard code it or you do additional experiments to let it learn, but it needs to learn from failure as much as it learns from success. And so for those 6, which are really in sort of, the top corner of the formulations that we got, they have a really good bridge margin and a very small amount of line edge and line width roughness, so the wiggles that you get in the line basically at the edge. There are dozens of points from sequential learning that are what I like to call out in la-la land, like totally in the wrong part of the space. And that was an important part of the process because the model sort of learned which formulations worked and which ones didn't, and that's how we got there. But in the end, I mean, even more importantly than that, we did find these 6 formulations, which worked really well, but we also have a bit more understanding about some of the parameters that make the most sense. We have confidence about those parameters because there's ones that we kind of know about, that we recognize, and okay, this is cool. But there are also surprising ones that we were like, I hadn't thought about that one before. And that's really led us into sort of new creative directions from the experimental side as well. And so you can talk about the numbers, like, oh yeah, we achieved this bridge margin, this line width roughness, this many formulations that worked. But it really was this sort of this innovation cycle that got kicked off again by using this platform, which is really cool. So
it's funny. I'm very lucky. I've got some nieces that are now growing up a little bit, and I've started to think about these machine learning algorithms as very much like teaching a child. And so somebody was asking me, like, how do we make the model better?
Yeah.
And my answer was always a little bit unsatisfying, which is you have to do some of the tests that the model, or at least something close to the test the model is suggesting, because for anyone on the webinar that has kids, that you don't sit your 2 or 3 or 4-year-old down in your living room and give them a 1-hour lecture on how to ride a bike, and then put them on a bike and have them do it, right? Like, that's not how you train models either. Yeah. You can teach a little theory, but you need to sort of let the model make some mistakes and learn, and it learns quickly, which is great. But the other thing that you said was around this idea of new learning. Mm-hmm. One of the things that makes me happiest about when someone is using our platform is when there's a scientist with a ton of experience who looks at one of the predictions or suggestions or any piece of the platform and says, that makes sense to me now, but I never would have thought of it.
Yes.
And that means if AI goes away tomorrow for some reason, you still have a scientist who has something they've learned, and that, especially when they're the folks on your team and on the teams adjacent to yours are no slouches, right? These are not people who are like stumbling about in the dark. They're brilliant scientists. Yeah. To help them learn is also, it just shows that there's really a nice symbiosis here. But so as you worked with those people, right? Yeah. If it were you, I have the impression you'd be just jamming on AI and doing experiments and feeling good. But at every company we talk to, it's okay, I want to know the technology works, and then I want to know that we can adopt it.
Yeah.
What were some of the challenges and kind of how did you make the decision in the first place?
Yeah.
To embark on this technical but also cultural journey?
Yep. So, I mean, our journey with Citrine started years ago, and this was not the first project that we tried. There were multiple others that came before. And those others really set the groundwork for what types of problems do we think we really need the most help with, where Citrine is delivering the most value. So, at EMD Electronics, we cover the whole semiconductor manufacturing process from a materials perspective. So we really tried in all of those different divisions, what would this do? So we worked on everything from single molecules that you might find in our specialty gas business or our thin films business through to the formulated products in chemical, mechanical, planarization, and patterning. Mm-hmm. I think where Citrine wound up being most powerful for us was a space where you didn't have technical experts that had been around for years, that had fully optimized a space already, and then you tried to do a bake-off of Citrine versus those experts, because they really had clued into a lot of stuff that we couldn't reflect in the model right away. They would win in that very quick bake-off, and then they would be like, okay, I don't need this, right? That was the end of that journey. Really, where we found that the adoption was highest was when it was one of these really complicated spaces where you needed to not only know about the individual chemicals, but how they were interacting with each other. And I think that's where a lot of the chemists sort of go, it gets just too complicated for the human mind to deal with. And also a space where there's pressure from, customers from the market to be delivering really quickly, and where honestly the cost of doing experiments is very high, right? So in that magic cluster of all of those things together, that's where we got to where we are. But it was really this sort of shift where, in some of those early studies, people were like, listen, I'm under the gun from my customer. I literally won't do experiments that I know won't work. I just can't. And so you need to find that right balance for your early adopters, especially, where they're willing to do those experiments and where it really brings them benefit to do those experiments, because maybe they don't know if it's going to work either, right, at that point. Yeah. So those were some really important things, I think, that set the stage for us finding success. One of the biggest markers, I think, for success is when you feel the culture shift really subtly, and it's just in the way that people talk. And so when people were setting up new experiments to do, right, the old language was, well, let's try this because I saw this trend, that increasing the fraction of the formulation for this chemical was going to be better. Mm-hmm. And now what you hear is people saying, well, the model is showing that the likelihood of improvement is best for these 5 samples. And so they're using the language of exploration and exploitation, optimization in the space to really talk about the candidates that are coming out of the Citrine platform, recognizing some of those are exploratory and going to fail. Some of them are more exploitative and are likely to succeed or at least be closer to the target. Mm-hmm. And it's those sort of subtle shifts that people are interacting with this platform. It's something, we always talk about artificial intelligence, and we have a word at my company called materials intelligence, which is the physical part. Yeah. I like to talk a lot about sort of convergent intelligence, where it's seamless, right? It's you're not using the machine to do stuff. You're not using the humans to do stuff. It's this conversation between the two that's really bringing the insight. So, to me, that's sort of, it was overcoming those initial hurdles of people being like, I just don't want to do this. I know these are not going to work, and I know, I am under the gun. And the model, I have to tell you about this. The cult of model accuracy. Oh gosh. That was a thing, right? So when you build simple statistical models for systems that are linear, you're expecting R squareds of, 0.9 is kind of fine. And then you're seeking 0.95, 0.96. Right. When you do the R squared of these very complex models, and for all of the models in Citrine, I just want to tell people out there, it's they were 0.6, okay? And then you look at that at first, and everyone looks at that first, and they go, ha! They freak out a little bit. And then they go, this model won't be able to tell us anything. There's so little signal. And then you just have to go, listen, when you have 0.6 and you look at the cluster of points, it means that you're starting to be able to understand which things are good and which things are bad. And it's pointing you in the right direction, even if some of the errors on those points are large. And with every cycle, you learn and the accuracy becomes better. Or you decide, I've topped out on accuracy and I need to bring in more experimental points, a new chemical space. We did that 2 or 3 times, and that was really critical. In the 10 or 11 cycles of learning to get to those 6 awesome candidates, there were a lot of points where our model saturated and it just wasn't giving us anything new. So we're like, okay, we need new chemistry to bring to the table. We add a little bit more, model started learning again, and then it moved forward. The other thing is descriptors. So y'all have a lot of really great descriptors on the platform. There's 100 and something, right? Even more than that, probably. Yeah. And those descriptors are really quick to calculate. They give you some good information about individual chemistries, but we also have more sophisticated descriptors, right, that we could do using density functional theory, or actually more exciting to me is these AI approaches to density functional theory, where you can actually quickly, on the same time scale, in seconds or minutes, get, lots and lots of data points.
Surrogate models and that kind of thing.
Exactly. And so when we add those into the platform, that also helped enrich it. So I'd say it's if at first you don't succeed, it doesn't mean it will never work. It just means that, okay, what's happening? Why do I need new experiments, new chemistry, new models, new descriptors? There's lots of options to try. And honestly, the descriptors are the biggest thing. That's one thing we realized. I gave you such a hard time in the beginning because you have a random forest model, which is the main workhorse model, right? Which is actually very good for a lot of classes of problems. But I'd have scientists on the data science side coming to me and be like, "Where is their XGBoost model? Where is this other model?" Like there aren't like millions of models on the platform, or even dozens of models.
Like 5 or 6 or 7. Yeah. Depends on the problem, but yeah.
But to us, when we started going, actually, for a lot of these screening activities in particular, random forest was just fine. It's the descriptors where you need to make a lot of improvement. And so I think that's the thing, right? Like, yes, we would love to have, I'm still going to give you a hard time that we'd love to have more models on the platform. But at the same time, we realized that to get us where we need to go in the real world, it was the descriptors that were really, really important. And that came both from your side and from our scientists being able to upload them. So
yeah, look, I mean, my thinking with this stuff has always been, if I could just go, and me and my team, if we could just go and do everybody else's chemistry better than everybody else, we would just go compete with every chemical company on Earth. That's not our goal. Our goal is to create a really long lever for EMD Electronics and your brilliant scientists to get more out of your team and out of your company, not to try to have a complete photoresist optimization system out of the box. That would be alarmingly specific, I guess is the way I would describe it. So can you talk to me a little about, I mean, you know, obviously bringing people around on the technical side is really important. How did you think about that? Did you start with, a handful of folks that were really enthusiastic about ML and AI, and I use those sort of interchangeably, just for clarity. Did you go find a particular project and then sort of browbeat those scientists? Did you find a hybrid of the two? How did you get to a point where people were willing to listen? Because that's always the hard part.
Yeah, I think that, there were elements of just trying it in a lot of problems. And one of the earliest projects that we tried was in our display division. It's now called our optronics division at EMD Electronics. So besides our semiconductor portfolio, we have a huge amount of materials in the display space, so liquid crystals and OLEDs. And those are becoming important for all kinds of other interesting applications besides televisions and monitors and stuff. You have the AR and VR space, which is really opening up now. So
it's going to be a huge market.
It totally is. And sort of what's old is new again, right? It's like we have all of these chemicals sitting on the shelf that really could be useful for these new technologies, but they're new properties that we have to predict and stuff. Sure. And that was when we really made these discoveries that, gosh, there are some properties that we weren't, even with databases full of materials, able to predict back in the day. But when you start to put chemical descriptors on each of the materials in the formulation and then calculate formulation descriptors on top of that, that really started to move the needle where we were able to predict. And that was it. So we tried a bunch. Some of them, bake-off was lost. Some of them, there was a new thing that emerged. And if you try a few, I wouldn't just show up in the first place and just do, one. I would do a couple. And your team was really helpful in helping us select, which are the best ones to try with the appropriate data densities, chemical intuition and knowledge and so on. We got that early success. And that early success went on to other success, right? And so it was going, hey, this can work for formulations. And that really opened the door for the formulations business to come on board. Then when EUV started getting good results, there were other patterning projects that were like, hey, I could use that too. And then when those patterning projects came on, then there was early R&D stuff that happened on the planarization side that came on and said, hey, we can do that too. So when people are able to, for lack of a better word, see their science in what's happening, it made it all happen. But really to get there, it was, finding these early adopters. It was interesting. So this is a sort of a cultural thing. When we were trying to select projects for digitalization, there would always be this way of choosing that was based on sort of business outcome all the time, right? Which ones are going to give you the best outcome in the long term, most strategic projects, and so on and so on. And a lot of these are. I mean, EUV is obviously very, very important for us and for the whole industry, as a matter of fact. But those early projects, some of them were quite small, but there were also people who were really willing to try. And I think that was really important, is that, from a management perspective, if we made all of our decisions sort of on the non-functional requirements, the sort of, like what's happening in the business space, how strategically important is this? We might choose projects where there's a lot of knowledge that's built up already, a lot of science, maybe a lot of resistance to change for various reasons. But choosing some of those smaller other projects that were kind of newer at first, where they really could use any leg up and wanted it, that really said, that set the stage for all of these other projects that were, more entrenched, where there's more history, whatever it was, to go, I could use that too. So I think that was it. It was really a combination, but it was about those small steps, and every small step, celebrating it, socializing it.
Yeah, I mean, that makes perfect sense. I mean, we've seen it play out in both ways, where it's like we're just going after strategic major projects, and sometimes those are successful out of the gate, game changer. Yeah. But they're strategic for a reason. A lot of times they're pretty high risk, and so having that be the first place you go means there's a lot of risk involved. Yeah. So now that you've gotten to this point, what is your team's attitude now? I mean, are there a bunch of people who are like secretly going to the break room and grumbling about how, God, I can't believe this computer was successful, or is it kind of are you seeing a cultural sea change?
Yeah, I mean, I think that it's, like I said, it's in pockets, right? So you have those first drops in the pond that are creating these ripples. And, from there, it is branching out. I really do see that. I think it's interesting, right? Like, people are very much anthropomorphizing the model. Like they're talking about it like it's one of the other scientists, for better or worse, which is really fun.
This model doesn't have much of a sense of humor.
Yeah. And so I think that's really interesting. But in the end, yeah, like, I mean, I think one of the other big things that maybe people talk about, maybe they don't, is there is not a chasm, but like a small divide in between sort of the two spaces, right? Between the digital space and the experimental space. Yeah. And what seems easy for folks on the digital side, like, just write a Python script and do that thing, right? Yeah. It doesn't come easy to a lot of folks. And so the more intuitive you can make it, the more projects that you can bring on board quickly. So we recently brought on board, another project in our formulated material space on the planarization side. And those folks, were really lab scientists just getting onto the platform, had a very tight timeline to deliver. And within a couple of weeks, they were playing around building their first model. And it was really, they went to Citrine University and did that. It was really exciting to see, right? And we've already gone through 2 cycles of learning on that project, which started, maybe a month and a bit ago. And so it's been incredible. Tested a lot of materials through that already. Already have a couple of points of success on that one early. And so it's been a really amazing journey. And I think that's part of it is just, making it easy for people to get on board, and removing those barriers has been just as important as making the back of the technology really, really good. So
you mentioned kind of the folks who are digital already.
Yeah.
And I guess that prompts two questions for me.
Yeah.
One is, this sort of boundary between theoretical and experimental, right? Like when I was an experimentalist, I was always like, a little bit, and it's funny because my co-founders were both theoreticians.
Yeah.
I always took that as like, I mean, you can tell me what the theory is, but I can tell you what reality is.
Yeah.
And so there was always this sort of, it wasn't tense, but it was almost like, which is more important, physics or the experiment?
Yeah.
And I think it depends on the domain. So that's one question for you, and then I'm going to queue up a second, which is, EMD is a big company.
Yeah.
You guys have a lot of resources. You're obviously a really smart, digitally oriented person. Like, did it ever cross your mind that, like, hey, we should just build this internally and have our own tools? So I guess, sort of the digital world at EMD, how do you think about that?
Yeah. I think that, when you think about the digital folks in the digital world, like, the good thing is that computational chemistry has had a very strong footprint in our company for a long time, right? So EMD Electronics is part of Merck KGaA, Darmstadt, Germany, 350-plus-year-old company that started around the idea of quality in pharmaceuticals. And we have these 3 divisions now: healthcare, life science, and electronics. And electronics is kind of the baby, honestly. I mean, we've been doing the other ones for a lot longer. And AI and machine learning in those spaces has been really sophisticated, right? I mean, you had this past year in the Nobel Prizes, AlphaFold was recognized, and that was built. An interesting thing about AlphaFold that a lot of people maybe don't talk about is, from an algorithmic perspective, from a digital perspective, you geek out on the idea of how AlphaFold works, its inner guts, right? Like, how is that architecture built and all of that? But AlphaFold wouldn't really exist if it wasn't for 50 years of curated experimental data on protein crystallography.
Yeah.
And I think that's the thing that when you realize that and you celebrate it, that it takes all of this physical information to inform these digital models, and those digital models can in turn, as I mentioned, feed back to the physical world and say, oh, the parameter of your molecule that's really important is this, or this ingredient in your formulation is having a really unexpected result. Or the biggest surprise for us was, take this molecule that performs kind of terribly on its own when it's in the formulation, and combine it with this other molecule, and you get synergy and magic that basically happens. And not just that, but like having a teeny bit of understanding, and we're just starting to have that understanding of why. Those are the things that really can break through all of those barriers. And making the technology accessible is really important. So we do have open access projects on Bayesian optimization, for example, that we've released to the world. So we aren't developing this in isolation, and it isn't an either or. It's not a build or buy. It's like, there are successes that we've seen with your platform that we'll use that for. Our Bayesian backend, super awesome. We've launched it to the academic world. We're using it in different parts of the company, for specific purposes. And so I think that's the thing also, that like there is sort of a false dichotomy between, well, I already have a tool to do that. And I don't think that that's necessary. I think that, it's just about finding the right fit. And I think the biggest thing that you all have going for you, chemical awareness, plus the idea of this very friendly interface, right? That people can really talk, not actually talk to, maybe soon, but talk to.
No promises, in theory.
But really have, like I said, these sort of very intelligent conversations with to understand and interrogate data and see things in a new light, right? And so that's been a really cool part. But it doesn't have to be either or, and it doesn't have to be a divide.
Yeah, no, and that's good to hear. That's a different perspective than I've heard from other folks, where it's like, no, I have computers and computers do math, and so I'm going to do this one kind of math. But you're right. It's you got to find the right tool for the job, and sometimes it's a manual screwdriver, and sometimes it's an impact hammer, and anything in between, right?
Yep.
It's an important thing. Yeah. So I know we're getting close to the end here. What is your vision for the future? What do things look like? What does the project of the future in 2025 and beyond at EMD look like? And what are the things that you would offer as advice for people who are starting on the journey just now or might be in the near future?
Yeah, absolutely. One of the things that's really been exciting us is generative AI. And I don't just mean chatbots, and I don't just mean image generation. I mean generative AI for chemistry. And generative AI for chemistry all follows vaguely the same formula, which is that you build new molecules computationally, and then you score them. You figure out, okay, how are they going to do? Mm-hmm. There are fast ways, as I mentioned, sort of in the modeling space to do that, right? So you can develop these computational descriptors. You have many of them on your platform, for each individual ingredient. We have other ones that we've developed with academic partners and so on to score these molecules. But again, we need to get closer and closer to scoring them not on just individual chemical properties, but on how they're going to perform in the final formulation. And that's an exciting thing where I think that, hybridizing this sort of generative AI framework of trying new molecules out, and then linking it with something like your platform where you're actually able to screen formulations virtually and try and predict how they're going to perform and feed that score back. And not just, we haven't talked about it much, but not just the score, but the uncertainty around that score, which you can also use as a score.
Yeah.
Really interesting, right? And so that's what I see a lot of the projects of the future going around that idea is, can we branch off into new and unexpected chemical spaces by really leveraging sort of creativity with very good scoring functions? And that's an area where I see that, these kinds of things will develop. And I think that the whole industry might be moving that way. When I think about how people are getting started, when you want to get to that ideal of actually being able to literally have your computer tell you what to make and then maybe even help you make it, right?
Yeah, totally.
The developing the scoring functions, that part, like AlphaFold, like having all of that history of data, is about making those individual models that are able to give you accurate enough predictions that you can actually use them as scoring functions. And so starting along the journey with take a simple problem, then make it a more complicated problem. Bring in and infuse knowledge, don't make it bake-offs, really try and make it synergistic. That's what I think everyone should start doing. And maybe they come to your platform. Maybe they wind up going a different way. It's all about finding the right fit. But I think our whole industry benefits from people becoming more digitally aware of what tools are out there, figuring out which ones are the best fit. And then once they find the best fit, socializing it. And then that will just get more people to come on board. And it makes it honestly easier for us because when we go talk to our customers, right, about the work that we're doing and how we're doing it, it's much easier to have a customer that understands, okay, in these complex spaces, this is a very interesting new approach that you all can use that isn't just changing one thing at a time. And we dig that. It's cool that you're changing this. It's cool that you're making mistakes. And so I really think that's the best advice I can give is just to start small, but also just not to give up as you hit the bumps along the road because every step in sequential learning, without fail, across all project successes and failures, we learn something. So,
I cannot think of a better point to end on. Enough said. Vijay, thank you so much for being here. This is both inspirational for me because, gosh, the number of successes we see with a lot of folks we get to work with is huge. The number of people that are willing to share them like you are, I'm so thankful for your willingness and your team's willingness. And I know that your experience is going to be really helpful to the folks in the webinar today. So we do have time for a few questions. So if you'd like to put those questions in the Q&A section on Zoom, Vijay and I will take a few minutes to answer. And we look forward to a robust discussion because I think there's some good lessons learned here and even some challenges that Vijay raised and, I think some exciting things coming in the platform over the next year or two. So thank you again, Vijay. Really appreciate it. And thank you for your time.
Thanks again for having me.
Of course.